Chapter 8.4 is about the ratio test and the root test. Let's take a look back at a geometric series. So r to the 0 plus r to the 1 plus r squared plus r cubed, etc. Let's see what happens if I take one term and divide it by the previous term, or one term and divide that into the next term. You could say like r to the 4, this term, over r to the 3 is just r. You could also do that over here, right? You could say like r to the 2 over r to the 1. That's also just r. So in general, you could say that the next term over the this term, or the present term, you could say, you could say if a sub n is the present term, then a sub n plus 1 is the next term. That's equal to r if it's a geometric sequence or geometric series. And we know that the geometric series converges if r is between plus and minus 1. So if the absolute value of r is less than 1. I want to emphasize this notation here, a n plus 1. I do not mean a sub n plus 1. I don't mean just take the current value of a sub n and add 1. I really mean the next term in the sequence after a sub n. So for example, if n equals 3, a sub n plus 1 is equal to a of 3 plus 1, which is a of 4. So if n equals 3, what we're getting is a sub 4 over a sub 3, for example. And then if it's purely geometric, then we're also getting a sub 4 is r to the 4, a sub 3 is r to the 3. So geometric series, we like them because they're fairly simple and it's easy to tell whether they're going to converge or not. So not everything in the world is a geometric series, so I've been told, but plenty of interesting things are close enough to a geometric series that we can apply geometric reasoning. So let's start reasoning by analogy. I love reasoning by analogy. It's like my favorite thing to do. If a series behaves kind of like a geometric series, in the long run, maybe the same convergence test applies. So what would that mean? We'd be taking a sub n plus 1 over a sub n. For a geometric series, that would always be the same value. It would always be r. But maybe in the long run, for large values of n, for some other series, it would be pretty much the same thing from term to term. So we're going to say take the limit as n goes to infinity of that fraction. Let's say that's some number. We'll call it L. Which we would hope is some constant. And that's basically the same as r. If the series is geometric, then it's exactly r. So we can apply the same convergence test. We can say if L is bigger than 1, then the series, well, like a geometric would diverge if r was bigger than 1, so then the series diverges. If L equals 1, we're going to say that's a mystery for now. We know a geometric would diverge, but we got to look into this later. Geometric would diverge. If L is less than 1, then the series converges. And here I've only been considering positive L. That's because our book makes a simplification, which is fine with me, and says let's only use the geometric series, let's only use this thing, this is called the ratio test, when the sequence we're considering is all positive. So if I had negative values, I would get a negative, like if it alternated in sign, like plus minus, then each time I'd have like a minus in the numerator and a plus in the denominator, or vice versa. L would be always negative. Some books deal with that by putting an absolute value on this ratio, so you can just throw out the negative. Our book says, let's only apply this to series that are already all positive. So here L can't be negative because we'll only apply this to series that are with all the terms positive. Well, note briefly what other books do. They do the limit as n goes to infinity, the absolute value of an plus 1 over an. But you know, why deal with absolute values if you don't have to? So this idea, take the ratio of one term to the next term, see how that behaves in the limit, and treat that like the r value from geometric. That is the ratio test. So let's go try the ratio test on a problem or two. Oh, one thing I forgot to say. The series converges or diverges according to this. Will it converge to 1 over 1 minus r like in the geometric? Probably not exactly the same, maybe kind of close, hard to guarantee. So let's write here, but the final sum is going to be often not equal to 1 over 1 minus r, or since we're treating L like R, 1 over 1 minus L. So it's going to be a lot harder to figure out how close it should be, but we shouldn't at all try to guarantee that it will be the same. And one other thing, this L less than 1 is including 0. So if L is equal to 0, that counts as being less than 1. I know in the limit comparison test, L equals 0 meant all of a sudden you had to say, well, maybe the limit comparison test doesn't work. But here, if L is 0, that's perfectly fine. It's just included in that case.